optics person would think about light fields and formulation and so on, now we have the answer for a computational photography person. Right? So he's talking about light fields from a computer vision, computer graphics point of view. This is Paolo Favaro. It's my great pleasure to introduce him. This will be the last talk for today. Don't worry about it. We'll have many more talks tomorrow and the day after.
Oh, yeah, so
you should definitely attend those as well. Paolo got his PhD from Washington University, St. Louis in 2003, and he is now a faculty member at Heriot-Watt University in the UK and an honorary fellow at the University of Edinburgh. So as I said, his research interests are in vision, computational photography, machine learning, signal processing, and so on. And he brings in a very unique perspective on how to create light field imaging. So.
Thanks, Srinivas, for the very nice introduction. Thank you for having me here. So today we will look at the portable light field camera, and in particular we'll see how that can help you get better images than with conventional cameras. So this is joint work with Tom Bishop, my postdoc, and is a collection of several works we put together here. If we look at how the current cameras are designed, then pretty much they follow the structure of the human eye. And this prompts a question, which is this design optimal for all vision tasks? Well, if we look at nature, actually there are several other designs that have been introduced and by evolution. And in particular, we can see that, for example, depending on the size of the animal, depending on its survival objectives, or depending on other constraints, like, for example, their computational capabilities and so on, nature arrived at very different structure for the visual sensors. So then this leads us naturally to the computational photography paradigm, which is, can we look at the joint design of both cameras and processing algorithms to actually get images that are better or satisfy some additional constraints that we may want to introduce. For example, we may not want to replicate exactly the way the human eye works, because, for example, we may not want to move the eye or change the shape of the lens to bring something in focus. Then under these constraints, can we actually design a different system that will give us a blurred or coded image, but then we can process with some blind convolution algorithm to obtain an image that is sharp. So as an example of this system, we can look, for example, at coded aperture photography. The idea is quite simple. You want to introduce a mask between the lens and the CCD sensor. It could be a fixed mask, or it could be an LCD, which allows you to change the mask as you want. Here's an image that we capture with a 4-hole aperture, and it's blurred. And it's blurred with this kind of coded blur. If you now, and the purpose of coding the aperture is that it makes it easier to identify the scale of blur in the image. Once you run algorithms to identify the scale of the blur, then you can use them to actually restore the image. And here's a magnification of a detail. This is how blurred it is, and this is how much you can actually restore it. And here we use one of our latest algorithms for coded aperture photography. But not only can you obtain the sharp image of the scene, you can actually take the blur scale estimate for each point in space and the sharp image and perform other tasks like digital refocusing that you must have seen very, very often in computational photography. And here, let me go more slowly through this. So here we have the castle, the glam castle in focus, and as we change the plane in focus, we bring the foreground, it becomes sharp, and the rest becomes blurred. We can do all of this basically by using the information we gathered from a single image. So in this presentation, I will focus on the portable light field camera, originally introduced by Aliasing and Wang. And I will look at what one can do with it, how one can actually extract information, how the system works, and I will also look at the limits of this system. So let's start from what one can get from the light field camera. So this is an image obtained with a light field camera. It doesn't really, it's difficult to see what this image is about until we zoom in and we can see the structure of the microlenses. From this image, one can actually obtain 3D, and this is a depth map that I encoded with intensity values, where bright intensities correspond to points that are close to the camera and dark points that are away from the camera. We can also obtain a sharp image of the scene. And then, as I demonstrated with the coded aperture photography, you can actually perform refocusing. And you can do that digitally. But more in general, you can perform some other tasks like advanced 3D editing, because we have both 3D and the sharp image. So, of course, in this arena, there's been quite a lot of work. The light field camera was introduced originally by Aliasing and Wang in '92, and they used it for depth estimation. Then later, Levoy and Ren and G used it for digital refocusing, and then they applied it also for 3D reconstruction of transparent objects with microscopy. In Stanford, again, Kaif and Elgamal introduced the multi-aperture integrated sensor, where basically they built a sensor that integrates the microlenses and also demonstrated 3D reconstructions. There is also work on several other devices that achieve similar objectives, like the programmable aperture camera of Liang and Liu. And the idea is to use the principles of coded aperture photography, where you have an LCD and allows you to capture several images with different types of masks. And also the heterodyne camera of Ramesh and Raghavan allow you to do similar objectives. And by the way, for all these coded aperture systems, the main limitation is simply that introducing masks basically eliminates light from the system. So while in principle they're actually very nice solutions to this problem, they actually are less light efficient than what I'm going to talk about today. In other areas like compressed sensing, there is also work that basically demonstrates how one can use these basic principles of compressed sensing and using sparsity, exploiting sparsity of signals, to build systems that need very few pixels to actually build a much higher resolution image. But so far, these are just prototypes, as far as I know. And of course, there are also techniques for obtaining sharp images by changing the optics so that the system does not really depend much on the depth of the objects in the scene. And so you can perform a simple deep blurring to restore the sharp image. However, for the basic system of the light field camera and the work of Levoy, one captures an image that is about 16 megapixels and performs digital refocusing at this size, which is about the size of the microlenses, and you have a 178-fold loss. So if you have actually an object that is non-Lambertian and is in the most general case, that's all you can really do. However, in general, we have objects that are mostly Lambertian, and it seems that also going from 4,000 by 4,000 to a 300 by 300 image, it's a big loss. So it looks like we would like to do better than that. So what I'm going to talk today about is how we get the digital refocusing, all the other applications at the full resolution. And of course, there is related work that aimed towards the same objectives. Particularly, there is work by Levin et al. On doing super resolution with 2D light fields. And most importantly, at the same conference where we presented our work on how to do super resolution, or better, full resolution of light field images, that's been worked by Lumsday and Georgiev. Their method actually is quite interesting because it's very efficient and very, very simple. The idea is that, if you remember in the image of the light field camera, we had all these little disks. Now, if you take one of them and then extract the center and zoom it in, and do the same for all the other disks, then you get the super resolved, pretty much the super resolved image that they get with their method. Of course, there's a little bit more about it, like averaging and so on, but that's a basic principle. One of the limitations here is that there is no deblurring, and this scaling is not done based on the depth, which actually does affect the size of the patch you extract in zooming. And our method instead, as you will see later in the slides, performs all these operations, so we can achieve actually a much better quality in the reconstruction. And finally, I'd like to mention some of the work done on compound eye super resolution, but this is just simulated. And all the analysis that I'll present has not been done in any of these works. So first of all, let's look at light field camera, how it is basically made. We have used a medium format camera, an Hasselblad H2, and the digital back that we use is the same one that Renan G and Mark Levoy used. It's a Megavision, where we have an interface with a microlens array. So since this is the light field camera, then I need to briefly introduce what the light field is, but you must have seen it already in the previous talks. Anyway, in very, very simple terms, the light field is a representation of how light propagates in space. So consider an object and a sphere around the object. If you now illuminate the object with some light, the object will scatter the light around. And now if we sit on a point in the sphere and observe the object from a certain direction, and we do that for every possible position on the sphere and every possible direction, then we build a function that is called the light field. Because the sphere and the directions parameterized in 2D and 2D coordinates, then we have only a 4D function. Sorry. So if we now focus our attention on a small portion of the sphere, and we consider just a plane rather than a portion of the sphere, then we can look at the coordinates u and v at the bottom, the red line. And we can also consider a plane parallel to this with the coordinates x and y. This is a classical parameterization used for the light field in the portable light field camera. So if we pick any 2 points on these 2 planes, they will define a ray, and this is the intensity assigned to this ray is defined by the light field function. Now, what is the light field camera doing? Well, it's simply taking this 4D light field function and trying to map that on a 2D array. And the way it does that is by taking the coordinates x and y, and for each of these coordinates, storing a block of coordinates uv. So we have basically an array of a 2D array. Okay, so as you've seen before, you need to actually look a little bit more in detail at the system to understand how it works. We'll look in our analysis, we'll look only the geometric optics kind of framework. So now we consider a 2D section of the system where the main lens, all the optics in the front are summarized into a single lens. The microlenses plane is now magnified so that we can appreciate the effect of the microlenses on the deflection of the rays. And finally, we have the plane containing the sensor. So now, if we take a plane and we position it in front of the camera at the position P, and we put some texture on this plane, this will generate an image inside the camera on the conjugate plane P prime. And then this will again be imaged on the sensor and will generate our light field image. So for a plane in that position, that's the image we get. And it's easy to understand that that makes sense because if you look at a point on P prime, the same point is actually imaged under different microlenses. And indeed, if you look at the QR text, you will see that under each microlens, there are some details that are repeated in the nearby lenses. If we move the plane closer, at the point that the conjugate image goes exactly on the plane of the microlenses, then we have that each point on the conjugate image is just imaged by a single microlens. And that's what you see indeed in the image there. And if we continue with moving the plane forward close to the camera, then the conjugate image will be behind the image sensor, and this will result in an image like this, where basically each image under each microlens will be flipped in X and Y. Okay, so that's just to give you the flavor of what type of images you're working with. There is another interesting way of, well, relatively interesting, another useful way of looking at the images we capture that we'll use later on. So if we have a target image on the top left, then we have seen that the way the light field camera works is by imaging this in an array like on the right-hand side. And this corresponds to coordinates x and y and uv as shown in the array here. However, we can actually take all the pixels and rearrange them so that we can get the opposite kind of rearrangement, where we have the uv on the outside and x and y inside. And this is what we call the camera array view. It's just simply a rearrangement of the pixels, nothing more than that. If you zoom in, what you see is that each of these blocks actually is a small image taken from a slightly different vantage point, as if you were sitting on the main lens. So this will be useful for later on to keep in mind. So say that we take a light field image like this one from the database from Georgiev, and we magnify a detail. What we can immediately notice is that nearby microlenses will image a shifted version of the same detail in the scene. So the basic idea that we can come up with here is that we can make use of this redundancy. And we have this redundancy because this object in particular is Lambertian. So we get exactly the same type of intensities on different microlenses. But more in general, we can see this problem as simply another instance of blind convolution problem, because in the end, no matter what we put in the camera, as long as we use optics, is going to be simply described by a certain point split function, and then we get a certain image that we want to deconvolve with this point split function. So in the end, we can take this problem as a space-varying blind deconvolution problem as any other of these tasks, as coded aperture photography or any other variant of that. But here, what we want to do is exploit the fact that we have this particular configuration of the point split function and make it and use it to actually solve this problem more easily. And then this will amount to estimating the depth map of a scene. We'll see that in the next slide. And of course, these being all ill-posed problems require to introduce regularization. And the same thing also will be required to be introduced for texture estimation. So as I mentioned, the problem can be described as for any other imaging problem as with a linear model, where we have the light field image, where we have the point split function that is collected into this linear operator H. And this will be applied to our sharp image. And what we want to use here is a function that is simply a 2D function, because we'll make the assumption that objects in space are Lambertian. So there's no difference depending on where we look at this object, from what angle we look at it. And finally, we have some noise. Graphically, we can see this as, again, our input image is the light field. Our point split function depends on the depth map, and we can definitely model that by using tools of, for example, geometric optics. And finally, we can get also the sharp image R. So let's look at the first part, which is identifying the point split function. So we can pose that as an energy minimization problem, because if we remember the interpretation of the light field as multiple views, one can think of using stereo or multi-view stereo. So it seems to be a straightforward application of those algorithms from computer vision. And then one can define a data fidelity term that tries to match all these views. And second, one can introduce some regularization, like, for example, total variation, to make the solution regular. And finally, we chose to minimize that by using some of the latest techniques, like linearized Euler-Lagrange equations. But let's focus a little bit more on the fidelity term, which is the most important part here. So in the view-based image, we have several views that we want to match. And then we can build a cost functional of this type, where S is our depth map function. And in this energy, we have a robust norm that basically will try to tolerate also outliers. And more importantly, there will be our views, which will depend on what view we extract from the rearranged light field image. Finally, there will be some disparity map that will define the warp, and this will also depend on the shifts in the view centers. So all of these can be modeled exactly by looking at how each sample in the scene is projected into the camera. Now, if you try and apply this, it won't work. And there is a basic reason why this doesn't work. It's because although we can look at the camera array kind of interpretation of the light field, it's not the same thing as in the real camera array. And the basic reason is, I'm going to try to make it, explain it in simple terms here. So in the camera array, we have the plot on the left here, on the bottom left. We have a set of cameras, and the resolution of each, and we exploit the full resolution of the sensor to get our images. So the aliasing in the spatial coordinates is very small. However, because they cannot overlap, there will be some aliasing in the angular coordinates. Vice versa, in the case of the planoptic camera, you can actually interpret the way things are imaged in the planoptic camera as having a set of sensors that overlap, and also their CCD is as pixels that are widely spaced apart. So actually, what we capture is a very aliased image, and you can see that by looking at the image to the right. This is one of the views extracted from the light field image. At the bottom, I have magnified the detail so that you can appreciate that as I move to another view, there's a huge amount of aliasing. So if you try to match that, it won't work, basically. It will do something, but it won't be really good, because there is really quite a difference between these two views. So basically, our microlenses make view aliased, and this is because the high frequency content is new in each image. That's great news, actually, because if we want to do super resolution or, let's say, full resolution rendering, we need new samples. If actually they replicate the same samples, then it's kind of useless. However, they make our view matching difficult. However, if we look at the low frequency content, this is shared among the views, and that can be used instead to do the matching. So that suggests a very straightforward idea, which is, well, let's just simply do anti-aliasing. With the catch that this anti-aliasing depends on the depth. So we come up with an iterative solution to perform the anti-aliasing on each view. Once we have done that, then we can match them, and then we can get our depth map. So these are some experiments that show you that effect. On the left-hand side, we have the reconstruction or the matching without regularization, without any filtering, any anti-aliasing. The second image and the third show that this anti-aliasing filter actually converges very quickly to the final solution. And you can see that you can correct most of the incorrect estimates where actually you do have texture. However, there are many regions where you do still have artifacts, and that's because you're trying to match regions where there is a uniform texture. So you can't possibly align that, because any solution would do. So for that, you need to introduce regularization, and regularization will simply propagate the correct or the most reliable matches. And so that's what we obtain to the right. So one step further is actually in getting the depth map at the full sensor resolution. And and this actually, when you turn to that, you can get an additional constraint that helps actually in doing this. So let's take this piece of the light field image and let's zoom in on a detail. If you use Georgiev and Lumsdaine method, or a variant of that, you can actually extract all these high-resolution images by zooming on a small detail and averaging them. If you use the right zooming, then the image you reconstruct looks kind of smooth and looks like, although blurred, a proper super-resolved image. If you use instead the wrong depth, what you get is, like to the right, is kind of these blocky artifacts, where you get basically a gradient across different blocks. So then this suggests a very immediate constraint. You can actually have an energy term that tries to look for the depth that actually gives you the least gradient across the blocks. And that's when they're basically, you're using the correct scale to magnify these images. So this gives you one more constraint that you can use and gives you a better depth estimate. So these are some experiments we did. On the left-hand side column, we have the low-resolution image and the corresponding low-resolution depth map without regularization. And in the center column, you see instead the super-resolved image corresponding to the super-resolved depth map that we obtained as well. So again, in this image here, we have a number of regions that are very uniform and where the matching is very unreliable. However, if you look at the point of view of image reconstruction, whether you put together two samples that are correct and incorrect, as long as they have the same intensity, it won't make a huge difference. But basically, bottom line, there's nothing you can really do about that. And to the right, we have an example of an image, super-resolved image that's being reconstructed by using the incorrect depth map. And you can see there are some blocky artifacts, I hope. So finally, we have our depth map. We can define exactly the point spread function. So we have our big H, and we can now focus on obtaining the sharp image. And we use some image priors, because these are all ill-posed problems, so you still need to introduce regularization. We use this non-stationary image priors that's been proposed by my postdoc student, Tom Bishop, during his PhD thesis. And basically, to summarize what these priors do, they are actually specific to the image that you are restoring, and also they are local. So they try to estimate local statistics of the texture and exploiting those to actually get a much better, a much tighter description of the distribution of the texture. And that's indeed what they do. So let's see some experiments. This is one data set we collected, rearranged in this camera array kind of format. So it is much easier to understand. This is one of the views. And this is the depth map that we obtained from this single image. And these are the results that we obtained compared to, on the left-hand side, the low-resolution image, compared to Georgiev's method in 2009. And this is our work. And you can see that there is definitely a gain in sharpness in the way we do it. But there's much more, actually, that one can find by looking at these images. If we zoom in on this image, you might notice there is something interesting going on here. The image looks sharp everywhere except for the center. In the center, we have actually that things are blurred. And actually what you can see is that the blur has the size of the macro lenses. And indeed, you will see next in the slides, but what I can conclude now is the basic description of the light field camera is that it works exactly as an inverted depth of field compared to a conventional camera. That is, in a conventional camera, you have a plane in focus. As you move away from this plane in focus, things are blurred. In the light field camera, it's the opposite. Away from the plane in focus, things are sharp. At the plane in focus, things are blurred. And the blur is capped by the size of the macro lenses. So that's something quite interesting about this system. And then it tells you that if you actually move the plane in focus close enough to the camera so that the objects are all behind, things are going to be quite sharp. But let's actually not get too excited about this, because you'll see in the next analysis of the limits, there are some other limitations of the system. So actually you can see this immediately, this effect, by simply taking the analysis of the system, computing analytically the point spread function, and even with geometric optics, you can get that immediately the phenomenon is described by the blur under each microlens. So in this graph here, we consider a range of depths from 100 millimeters to 10 meters. We consider a system with a focal length of 80 millimeters and f number 3.2. And on the vertical axis, we plot the blur radius in pixels. So if we are below 1 pixel, we can think of having a sharp image. If we go beyond that, we have blur, basically. Now, for this configuration, with the plane in focus at about 365 millimeters, the light field camera has a blur that basically grows as we go close to the plane in focus, while the regular camera, the conventional camera, which is in dashed red lines, goes quickly out of focus, and that's because we have a very shallow depth of field. So clearly you can see there is some gain here from such a system. And of course this plot will vary a lot depending on which plane you pick in focus in space and all the parameters that you choose. But let's look a bit more at some of the, let's say, factors that tell us how well we can reconstruct the light field. So we'll consider basically, again, our geometric optics analysis, where we have several object planes, and this will be imaged in those conjugate planes on the other side of the lens. And now we will focus specifically just on this side of the camera, which is where we have the conjugate images. And that's because everything can be understood just by looking at this side. So one factor that we identify as very important for basically solving this task is what we call the repetitions. Basically, when you try to identify the depth, which is key to identifying the point spread function, you need to have your matching views. And the views to actually give you a match, they need to share, to be actually containing the same sample in space. Well, that means that different microlenses must observe the same point inside the camera. And that can be easily determined by looking how this point is blurred on the microlens array. And clearly, the more microlenses see the same point, the more matches we can get. But also, there is a limit on how beneficial this is. The most important thing is that we don't want to have too few matches. So, bottom line, to find the number of repetitions that tell us how well we can do the reconstruction, we simply take the blur generated on the microlens plane, and then we simply see how many microlenses fit under the blur. A second very important factor that will take me a little bit longer to explain is the magnification. So in performing the reconstruction of the sharp image, we need to use a common reference frame that does not vary with the depth of the object in space. So what we do is we pick the plane coinciding with the microlens array. Now, if we take an object in space, and this has as conjugate image the red arrow, what we do to obtain the image on the microlens array is simply by projecting this red arrow on the microlens plane by using the center of the main lens, O, as projection center. So that's just a representation, nothing more than that. But that is just to give us a common reference frame for any red arrow that will be actually shifting inside the camera depending on the depth in space. Now, if we look at how this red arrow is imaged under each microlens, for example, these two microlenses in the figure, then this will correspond to the flipped green arrows under each of these microlenses. And these green arrows will be imaged with a certain resolution that depends on the CCD sensor, pixels. But now what we want to do is we want to look at the resolution of the reconstructed image on the microlens plane. That is basically how many pixels actually we get eventually on the purple line, on the purple segment. And you can see immediately that as I move objects in space, then the red arrow will move in space. It will correspond to different scaling of the green arrow, which eventually will turn out into a different resolution for the purple one. Bottom line, basically, even if I say that under each microlens there is a certain amount of blur, this is not the actual effective blur, because this will be then scaled up and down or down by this magnification factor, which tells me that basically objects in space will be resolved at different resolutions. Their effective blur depends on their position as well. So this is another element to keep in mind. And actually, perhaps a way to look at several of these factors together is to look at the sampling pattern, which was introduced also in the previous slide, in previous presentations, and has been used also by other researchers like Annette Levin. So let's look at three conjugate images. The one in purple, we have some texture along this axis, so you can see that we can have different intensities. We have the red plane and the blue plane. Now, in this image, we have sort of this phase space with our notation where we have U on the microlens array and theta on the main lens plane. And we image U on the horizontal axis and theta on the vertical axis. So now, if we look at the image generated in this 2D plane by the purple plane, we can think of capturing, picking 2 points, one in the plane with U and one in the plane on the main lens by theta. And this will define an array that will intersect our object. And we'll pick a sample and place it in the 2D plane. And now if we look at how which coordinates actually pick the same sample, then we can see that this will span several coordinates that will vary sort of inversely with each other. As theta goes up, then U must go down, and therefore, and this will be a linear relationship, so we'll define a slope with negative value. Similarly, we can see that the red object will be imaged as a vertical pattern, because for any theta, we will be imaging the same sample captured by U. And finally, as we go towards the behind the sensor, then we can repeat the same process and obtain that we get a positive slope. So this is something that perhaps most of you are already familiar. But there's something else I wanted to mention here. Now, what happens if we take the plane, the blue plane, and push it towards infinity? Well, what we get is basically the slope 1 with slope 1, because then in this case the coordinates U and theta will be actually matching, because at infinity we get all parallel lines. So we can't and if we want to actually get slopes that are beyond slope 1, what we need to do is go outside in front of the lens, and this will be imaged inside the lens, so that we get the scene depths are closer than F, and we can get into the green area. Another observation we can do is that if we do the opposite, if we actually look at an object at infinity, this will be mapped inside the camera at the depth on the focal plane, on the focal length of the lens. And this will correspond to some slope that is the boundary of the yellow region. And actually, it turns out we can't go anywhere beyond this plane, because this will correspond to objects that are inside the camera and that are imaged inside the camera again. So these are not real objects. So that tells you that basically in the yellow region, you have some space that is not used, that is not useful. Perhaps you can actually try to generate your sampling scheme so that it uses this space where there are no real objects. So finally, let's look a little bit at how to understand what sampling of the light field camera does on our objects. So All the gray parallelograms that we see in the image to the right are our pixels and the integration region for each of these pixels, assuming they're all square. On the number of pixels that we get along the vertical axis are the number of pixels under each microlens. And on the horizontal axis, we have the number of microlenses. Okay. So here we have a small portion of that, and so that we can analyze things a bit more in detail. So if we take a ray of the same sample across the blue object, this will cut through several of the pixels, and every pixel will integrate a different portion of this ray. Well, what we get from this is that the same pixel will actually be blurred across the different pixels in our, the same point in space will be blurred under each pixel in the sensor, and the blur diameter will be defined by the projection of this slope on the vertical axis. So in the limit, when we have the red object, we have that the blur is as much as one can go, and is bound by the number of pixels under each microlens. So that's a very simple way to understand what we've observed already before. There's one more observation that is not really immediate obvious by looking at all these analyses. And that's the coincidence of samples and how this actually affects your reconstruction. So for the purpose of image reconstruction, you want your samples to be unique, if possible. But actually, if you look at the way all the samples are projected through the microlenses, you will find immediately that there are planes where these samples coincide. Therefore, each microlens, or some of these microlenses, will actually share the exact same sample from space. The same thing happens at this plane, the same at this one, and so on. And the worst case is actually this one, which we've already seen is the one that gives you the maximum amount of blur. So we'll see actually that this is something you can observe only when you perform the full image reconstruction. And we'll see actually how this will affect the performance. It will create dips exactly at those planes. So let's look at some experimental validation. On this graph here, we have the improvement in the signal-to-noise ratio. So we take R as our true texture, R naught as a texture from the low-resolution image, and R hat as our estimate. Clearly, the more we approach the true texture R, and the more the ISNR will be high. Here we run several experiments for different noise levels. Every color corresponds to a noise level. This is the method from Georgiev, the dashed lines. And these are the performance that we obtain with our work. As you can see, the more you add noise, the worse it gets. And there is a beneficial effect of the method of Georgiev of averaging all these samples because, of course, you reduce noise. But this happens for a quite large amount of noise. More importantly, you can see all these dips. And they actually coincide exactly where you have a coincidence of all these samples. And of course, also, if you look at the effective number of new samples, you will see that there will be, for each plane, a different performance because you have more or fewer microlenses sharing the same number of samples. You can also look at the similar plot done with the L2 error. And you can see also a comparison between, again, low-resolution reconstruction, the coded aperture by using the mask from Zhu and Ayar, and it's in dashed lines. The solid lines are the traditional camera, and this is the live field camera. So you can see that there is a gain for each of the noise levels, also over these the different alternative systems like the coded aperture camera. The important thing here is also to notice that in the middle, we don't have a value in the plot, and that's because that's where the image, the plane in focus for the main lens is. And for that, our performance, of course, drops to the low-resolution reconstruction. Okay, so last slide is a comparison with several other systems. And so you can show you that the live field camera actually has quite some benefits. And in particular, if you perform the full blind deconvolution problem, if you solve that, then you can get quite good results. So here we compare systems by using the exact same conditions. We match exactly the same noise levels, the same number of pixels, and the same objects in space. On the left, the left column, we have the light field for several planes at different locations in space. Then we have the results obtained with Georgiev. And you can see that we get some resolution, but it's kind of blurry. If you can then think of applying deblurring to the result obtained by Georgiev, you actually get the third column, which is a bit better, but has also basically doesn't resolve much more detail than what you can really get in the previous one. If you use our method, we can get much more detail in each of the images. And as you can see, as we move away with the plane in space, we also start to lose some of the resolution. And that's because of the magnification effect. And now we compare also with the coded aperture camera. Again, we have several planes, so you can see the blur increases as we move away. And you can see the result is not too bad, but we get actually quickly, we get more artifacts than in the light field camera. We also compare with the focus sweep camera. The idea in the focus sweep camera is basically that you take and integrate all the images that you collect by changing the focus setting of the camera, so that you're kind of capturing and adding up all the images for several focal planes. So this has been quite popular design or camera, because you can then do as in waveform coding, you can apply a single deblurring with the same type of blur and reconstruct a sharp image. However, as most of these extended depth of field systems, you don't have quite a really depth invariant PSF, because you're integrating over a certain range, and for planes that are really close to the boundary of the range, the approximation that you use is not really super good. So you get a reasonable performance, but as you go to the further planes, it gets worse. So to conclude, we have analyzed the light field camera with simple geometric optics, but we looked at several aspects, the sampling patterns. We've also seen some limits, and in particular, this coincidence of samples that I think wasn't really observed before. And we have introduced several novel algorithms for depth and image reconstruction from a single light field image. Now, you may think that, okay, light field image is a collection of images, so it's like a camera array, so it's like having multiple images. It's not quite like that. The way I see it is, this is a camera, as any other camera, where you modify the optics. And if you're smart about how you modify the optics, then it's still a single image reconstruction task, like you do with coded aperture photography and all the other kind of methods. And of course, this is a very ill-posed problem, so you need to define suitable regularization or depth in image priors. And this also, as was mentioned before, is something that tells you, if you look at the system as a single image reconstruction, and you want to obtain a depth map and an image at the same resolution as your sensor, something has to give. And clearly there is a trade-off, because you use part of the information from your image to identify the depth and part of it to perform the reconstruction. Now, you've seen that to identify the depth, you need to have some overlap. Some of the content in the images must be shared across the views, or in a way across the different microlenses. And that will be the part that is not novel when you reconstruct the image. So you give up some texture to be able to align them. And vice versa, if you try to preserve as much texture as possible, you will do a poor job at aligning them, and so you will still not be able to put together a sharp image. So something has to be given up in the process. Well, thank you for listening.
Time for questions? Yeah, please.
So on that, the slide where you made all those comparisons, can you say anything about how the effects of motion blur might inflate those results? I mean, I'm assuming in that case that everything was static.
Yes.
But if there were some kind of motion of the camera, will some of these methods suffer more than others?
Yes. So the focus sweep clearly will suffer from that, because you're moving the focal plane, and as objects move, then you will get actually that the image will be blurred depending on the motion.
No, sorry.
Yes.
It's not true. Tomorrow I will give it the other.
Okay. Well, it seems to me like a practical thing, right? You're integrating in time, so if objects move, then you're imaging the object in different locations.
It stays motion insensitive.
Sorry?
Because you do you can see its integration of different focal planes.
Yes.
You can also see its integration of different cameras which track the motion in different directions. And this way it stays motion invariant and depth invariant, the same.
Okay, in the conventional focus sweep camera, you do get motion blur because it's really very simple. If you actually take each instantaneous image, the object will actually be in a certain position and then it will move. So your images actually are really the addition of several. If you change the optical system so that it tracks the object or does something else, then yes, you may compensate for that. But in the conventional focus sweep camera, you get that.
Depends on the speed of the sweep.
Of course, of course. But no matter what speed you choose for the sweep, the moving object can be fast enough to actually get motion blur. Right, so there's no question about that. So coming back to the question, yes, that's one of the problem with this system. And in particular, I would say that to me, one of the most important aspects is that in the live field camera, you don't need to have any moving parts. So that may be okay for many designs, many systems, but in the case of, let's say, in some situations, you may not want to move things, you may not want to have to calibrate them and so on, because also motion will not be always perhaps the same identical one. And in the coded aperture case, you still get the same benefits as in the light field camera, but again, you lose light, so there's some other. Yes. Yes. Any?
What's the sensitivity to noise in this method? I mean, on some you throw away some of the light, obviously you will get more relative noise.
Yes. So in this case, we used exactly the same signal-to-noise ratio, take into account all these factors, like what is the effective aperture of the system and the camera settings. And these are the performance you can see for all these different ones. So for the coded aperture camera, is not too bad, I would say, but you still do lose some of the.
As the noise level increases,
yes.
you get kind of a threshold effect where the method breaks down.
Yes.
And is that different on the different methods?
Well, of course, it's going to be different for the different methods. I don't know what the performance is for the coded aperture or the focus sweep, depending on the different noise levels. We can do that, of course, but we haven't really done it. So I don't know what the curves will be exactly for those systems. But I can show you what we have here in this plot for the case of the coded aperture camera and the live field camera. And you can see that for these three levels of noise, the live field camera can do better away from the plane focus at about 100 there, which corresponds to 700 millimeters. So you can see the performance as that varies. We gain much more when we have little amount of noise. We start to lose a bit more when we have more noise. Yes?
I sort of realize the very practical issues with this, but I mean, really, in principle at least, you have access to this point spread function of your system.
Yes.
So have you tried to methods that rely more heavily on the prior knowledge of this point spread function?
We actually exactly define the point spread function and use that.
Okay.
We simply do that. We also try to estimate the point spread function from images directly.
So what works better?
Well, in the end, actually, we actually our model is pretty good actually compared to the real images. So we didn't find. We actually use the real images to calibrate the system because there is kind of you need to calibrate the intensity under each macrolens so that they do match. But basically, yes.
Does this work with the same PSF over the whole image?
No, the PSF varies depending on the depth of the objects in space, and the PSF looks pretty much like like this plot here, where is this? This is a PSF, for example. It's like a disk that has been reversed and split. This would be a simple pillbox function. And then in this case, it's flipped across the different microlenses. Yes?
It appears to me that while calculating your depth map, the model assumes that you're collecting information from different views.
Mm-hmm.
But then while doing your super resolution, you're inherently assuming that you're looking at it from one view.
Yes. Yeah, very, very good question. Actually, no, you actually can get the full resolution image from different vantage points if you want. It's fine. We choose the central view, but you can choose different angles. Indeed, that's a very good question because it gives me a chance to say that you can get a super resolved view and actually you can get also the parallax at the full resolution. As it was shown in the previous, in the presentation by Marcus, you've seen that you can get this kind of viewpoint change, but that was done at the low resolution views. You can actually do that at the full resolution sensor.
How would you explain this? How do you relate this with the angular spatial resolution trade-off that you mentioned?
Well, think of it in this way. You have the depth map, and you have the texture. You can generate any viewpoint you want, right? So you can see that it's possible. So I hope that already gives you enough foundation to say, yes, it's going to happen. Yes?
First question, if you add a coded aperture to a planoptic camera.
Which kind of aperture?
A coded aperture to a planoptic camera. You might use the goals of the pixel to feel the depth. You'll combine and integrate it in your map.
Yes, so we thought about this. The problem is if you put a coded aperture kind of a mask as a coded aperture for example the micro lenses, then you still get the benefits of a coded aperture photography, so you can improve the quality of the image, but again you give up some light. So we're a bit reluctant. I mean, for example, in Georgiev, in his latest designs on the cameras, he uses smaller apertures on each microlens, so you can get actually more focused images. But again, you give up light efficiency, so there's always going to be a trade-off.
See, most of the images have some black and white or all. Can this be done with
yes.
color, layer pattern?
Yes, of course. You're perfectly right. I actually asked my student to do that in color, but they will take so much time to do all this work and this processing that he decided to work with grayscale images, and then later on he couldn't be bothered to do them in color. So, but you can perfectly do that in color.
So then you subsample the image. How would that work with this method?
Sorry, what do you mean subsample?
Well, you have
the Bayer pattern.
Yeah, the Bayer pattern.
Sure, you can take into account the Bayer pattern and then also use that in the modeling for your point spread function, for example, so that you can place the samples exactly where they should be. So yes, you can do that in the same framework. We'll give you, for example, different point spread function per color, but slightly different, not very different. Yes?
About text estimation, I think you always specify reference viewpoint first, then do the text estimation square function.
Yes.
Will this cause any problem at the occluded area? So some of samples are occluded in this reference view, and some of samples are occluded in other view. So will this sample utilize in the final projection, the reconstruction, or the evaluation?
That's a very good question. So, so in our experiments, we haven't really challenged the system by using like very thin objects or so that they become almost transparent, or like hair, this type of objects, and that's actually what we are trying to do. But in all these experiments, what you can see is that the occlusions won't be really a problem for this kind of objects. In the end, if you use a suitable depth estimation technique that allows for all these matching to be done correctly and precisely around the boundaries, the depth map is sufficiently accurate for you to do the reconstruction. What really becomes tricky is the blinding convolution. What we have done actually is, for our task, is to take the point spread function and applying the clipping of the PSF at the occlusions so that you can actually get the correct PSF that you would get at the occlusion boundaries. But whether you get enough information to get the exact clipping or not, that is a bit tricky when you have very thin objects. Yes?
Related question. So if I understand correctly, the point spread function is derived from the depth?
Yes.
So would there be cases where the assumptions about the scene that are used in the depth map are not necessarily hold up or match the assumptions used in the regularization, the superresolution, so there could be some kind of a disconnect since they're not optimized together?
Well, I think that reconnects the previous question where basically you have occlusions. If you have, I think that as long as you have objects that are piecewise planar or piecewise smooth, then the reconstruction we get is good. And it's because we use the latest techniques for multi-view stereo or stereo. Clearly, if your object is like fur, then it will be very difficult to get every single detail of that. But that would be true for any other computer vision task or problem. So, I mean, we basically do as far as computer vision has gone in terms of reconstruction.
Do you see an opportunity to combine these into one big giant optimization to get a little bit
more detail? I mean, yes, it's possible to solve everything together, but I don't know. I think it's a bit tricky because so there is some work on deblurring by Anat Levin, where they argue that you should actually split the task in 2 steps because then it becomes more solvable. And I think this being again a blinding convolution problem, I think it may still fall into that category. So I'm not 100% sure that you can gain a whole lot, but it may be possible. I don't know, haven't really explored. So.
Okay, last question.
Yes.
This is really impressive work, and I have a follow-up question on the previous question. Do you have a feeling of how badly it would fail if you had more complicated BRDFs and the Lambertian assumption would break down, and also like the camera up the air? Do you just have a feeling of how bad it would be?
Well, let me show you something where you see some effect of this. The regularization helps a lot. So we wouldn't really fail miserably. Well, you can look at these objects. This one is very shiny, right? But you have to keep in mind that we are observing different directions from the aperture of the main lens. So as long as the object is Lambertian within this angle, then there's no problem. And for most objects, you have that even with shiny objects, it won't be a huge variation. So that will be fine. What you lose actually is that you don't get the shininess as it should be. It becomes kind of more diffused. But that's all you get, really. If you then give me a sample where you have objects with very high curvature and the normals are, then yes, we most likely will lose all the shiny bits. And the regularization will kind of average them together. But it wouldn't be a terrible image.
Okay, so let's thank all the speakers again. Couple of announcements before everybody leaves. I know that there's a lot of people standing here and so on. Tomorrow morning we're going to go to a much bigger auditorium, and that's the reason we are having the conference for the weekend, really, because we have that auditorium. So. Does everybody know how to get to the Gates building? Rashid Auditorium is on the 4th floor. If you come on Forbes Avenue and see this Gates building, which is this gray building with glass patches, you just enter that, and that's the auditorium, okay, from the street level. So the things start at 8:30, but the breakfast is at 8. So please do come on time. Great, thanks. Thanks, man. Great for breakfast, Sri.